Hey everyone, and welcome. We're often faced with simple choices, right? Is it A or is it B? But what happens when the real world gets, well, more complicated? Today, we're going to learn about the tool that helps us answer those bigger, more complex questions.
Think about it. Comparing two things feels pretty straightforward. But what if your choice isn't just between A and B, but also C, or D, or E? How can you be really sure if one of those options is truly different from all the others?
To answer that, we've got to move beyond a really common tool. If you've ever heard of a t-test, what we're talking about today is the next logical step in your journey.
Right, so the trusty t-test is our go-to for comparing the averages of two groups. It's perfect for asking something like, does website design A get more clicks than design B? But what if you have 3 designs? Or you're testing 4 different types of fertilizer on a crop? That's where the t-test kind of hits a wall.
And this is exactly where we need a more powerful tool. So allow me to introduce you to a statistical method called ANOVA.
ANOVA actually stands for Analysis of Variance. And believe me, that name tells you pretty much everything about how it works. Its main job is to act like a referee, looking for real, significant differences between 3 or more groups, all at the same time.
But let's cut through the jargon. At its heart, ANOVA is really just trying to answer one big question. Are the differences we're seeing between all these groups real, or is it all just random noise?
To make this super clear, let's stick with an example. Imagine a school wants to figure out which of 3 teaching methods is the most effective. They've got the test scores for students taught with Method A, Method B, and Method C. With 3 different groups, they need a tool that can handle that kind of complexity.
So how does ANOVA actually do this? What's the secret sauce that lets it look at 3, 4, or even more groups at once? Well, let's get into the big idea behind it all.
Okay, the absolute genius of ANOVA is that it makes a really clever comparison. It looks at 2 kinds of variation, or spread. First, there's the between-group variation. How far apart are the average scores for method A, B, and C? Then, it looks at the within-group variation. How much do the scores naturally bounce around inside any one of those classes? This is why it's called Analysis of Variance. It's literally analyzing and comparing these 2 types of variation.
So here's the crucial logic. What happens if the differences between the teaching methods are way bigger than the normal random differences you'd expect to see within any single method?
Well then bingo! That's when ANOVA throws up a flag. It's basically telling you, hey, pay attention. The difference between these group averages is too big to be just random chance. At least one of these teaching methods is having a significantly different effect.
It sounds pretty perfect, doesn't it? But there is a catch. ANOVA is incredibly powerful, but it has one really important limitation you have to know about. Think about it. ANOVA just told us that our teaching methods are not all producing the same results. That's fantastic. But it immediately leads to the next question. Okay, so which one is different? Is method A better than method B? Is method C worse than the other 2? What's the actual story here?
So which group is it? Well, ANOVA doesn't tell us. The best way to think about it is like a smoke alarm. The smoke alarm goes off and it tells you there's a fire somewhere in the building. That's super important information, but it doesn't tell you which room the fire is in.
So, if ANOVA is our smoke alarm, how do we actually find the fire? To pinpoint exactly which groups are different from each other, we need to take another step.
You can think of this as a 2-step process. First, ANOVA gives you the green light. It confirms a significant difference exists somewhere. Then, you need a follow-up test to go in and investigate further.
And that follow-up analysis is called a post hoc test, which is just a fancy Latin term for after this. These tests, like the very common Tukey's test, will do all the one-on-one comparisons for you. They'll compare A to B, A to C, and B to C to tell you exactly where the significant differences are.
Okay, let's wrap this all up and put these new concepts neatly into your personal statistics toolkit.
Here's the main takeaway, the thing to remember. If you're comparing the averages of just 2 groups, you're going to use a t-test. Easy enough. But if you're looking at 3 or more groups, you start with ANOVA.
And at the end of the day, both of these tools are trying to do the same fundamental thing. Help us find the real signal hiding in all the noise. They give us the confidence to say that the differences we're seeing in our data are meaningful, and not just some random fluke.
So there you have it. You now have the key to unlock more complex questions, to compare more than just 2 things at a time. So my final question for you is this. Now that you have a tool to spot a meaningful difference in a crowd, what will you go out and discover?